Welcome, Pat. It's great to have you with us today.
Good morning. Thank you, and it's great to be here. Have I shifted screens all right for you?
There we go. Terrific, Pat. Well, take it away, and we'll catch up with you at the end of your presentation, and we'll take some questions in.
Very good. Thank you. Here is our topic for today, as Henry mentioned, is to get sort of an overview of the technology of weather radar measurements and how it's evolved from the early days in the 50s to the current upgraded dual polarization that the National Weather Service is undergoing currently. And before I leave this slide, I want to also acknowledge the funding from the National Science Foundation primarily and Colorado State University that supports the CHIL radar. The overview of what we'll be discussing today is shown here, and I've organized things primarily around the different types of measurements that weather radars make. The color coding here is a bit chronological. The earliest measurements, and the ones we'll begin with, are basic power measurements of reflectivity. A bit later in time, the technology to measure radial velocities, the so-called Doppler velocities, was implemented. And these last three here shown in red are measurements that dual polarization radars make. The radar I work at, that Henry mentioned, is the CHIL radar facility. This is an aerial photograph of the site, which is located in Greeley, Colorado, which is about 40 kilometers due east of where we're sitting right now here at the State Climate Office in Fort Collins. And the name of the radar, it has always been a research system. It was originally jointly developed by two universities, Illinois and Chicago, and they put together the leading letters of those two institutions to get the CHIL designation we go by. The equipment is designed to be transportable. So this is a low-level, low-altitude aerial dome that protects the antenna. As indicated here, this is about 65 feet high. In the lower right is a picture of the antenna inside. This main reflector is about 30 feet in diameter, and here's two of my colleagues standing underneath the antenna. So this is a large piece of equipment. The dome is supported by external air that's pumped in, like many indoor tennis courts and so forth. The electronics equipment is housed in several semi-trailers that park around the base of the dome. Familiar with the general geography here, this is the border between Colorado and Wyoming, and this is the southwestern corner of the Nebraska Panhandle. A few areas we'll see in some of the examples. Fort Collins is here, as I say, about 40 kilometers west and slightly northwest of the radar. Metropolitan Denver is about 70 to 90 kilometers to our range of something like 120 to 150 kilometers. That's on the order of 75 or 80 statute miles. So with only one exception, I think all the examples I'll show you are from phenomena we've seen here in northeastern Colorado. The basic notion behind radar is depicted on this little slide here. The acronym stands for radio detection and ranging, and it's great cleverness. I mean, the word spells the same way forward and backward, and we use this sort of return echo principle to find the information we're seeking. The radar technology really became a practical state of affairs during World War II. And the underlying assumption here is there's other types of radars, but for the ones used conventionally for operational weather purposes, we transmit a very short duration, high-powered pulse of microwave energy. And that's depicted here by this little set of red lines here. So the radar only fires a pulse for a very short duration of time. These are microwaves, electromagnetic radio waves that leave the antenna and travel at the speed of light. And the plan is these microwave signals interact with a target, which then re-radiates a small amount of that incident energy back to the radar antenna. So at the moment in time here, the microwave burst is just about to reach the target. Short energy has been re-radiated by the target, and it's about to fall back on the antenna and be processed by the radar. For weather observation purposes, the wavelength we use, this so-called microwave radiation, is generally between 1 and 11 centimeters, which in inches is on the order of 4 inches. The CHIL system and the National Weather Service radars are operating at the longer wavelength end of this. Our wavelength is 11 centimeters. And so after we transmit this short burst of microwave energy, the radar equipment more or less listens for a delayed signal that comes back from the target. And here's this plot in the lower right corner. It's an example of that. So distance is across the horizontal scale here in kilometers. The vertical axis is the intensity of the received signal. And the way the antenna is pointed here, it's looking towards the northwest at low elevation angles. It's illuminating a high voltage transmission tower. So for the first bit of listening time, no signal comes back because the pulse hasn't had time to interact with the target and come back to the radar antenna. So we can convert the time that we listen to distance that the object is away from the radar, and so we get a nice sharp strong signal here that indicates there's some target that's returning detectable signal, and it's located out here at about almost 37 kilometers from the radar. Now, to make a useful picture of this return from the radar, typically we scan so that we can get an overview of where these targets are located. This is the antenna at the CHIL radar doing kind of a jerky, because I made this from just a sequence of fixed pictures. But the antenna is scanning in what we call planned position indicator mode here, which means the electric motors that drive the antenna are rotating it around the horizon. While the antenna is rotating, the transmitter is steadily firing this sequence of pulses. Between pulses, the backscattered signal comes back to the antenna, is processed by the receivers, and we can make this top-down sort of a view of where the targets are located, as you see in the lower right here. So these dashed lines here are at constant ranges from the radar, and the straight dashed lines are at constant azimuth directions from the antenna. And that target we were looking at on the preceding slide is this middle one of these 3 high-tension towers. So you can see by scanning the antenna, then that power line jumps over by 3 towers and continues on to the south. And these, in fact, are the 3 towers. These are by watching these microwave reflections that come back as we scan the antenna, the objects are that are returning the radar signals. Here's another presentation of our data zoomed in on the Denver area. This is metroways, these sloping lines. The main feature of interest is the runway complex down at Denver International Airport. And when the radar illuminates aircraft that are flying, they appear as these discrete little dash-like targets here. They're always long axes across the direction of the radar antenna is looking. Let me shift to my web page here, and this is a little animated sequence of the images we obtained by scanning the antenna over the airport. So you can tell that, for example, on this particular afternoon, departures are taking off from this runway towards the west. Arrivals are coming in and landing on this other runway up here at the northern part of the airport. Also, arrivals are being directed around to land from south to north. The point here is this was a demonstration of sort of the original radar technology during World War II. You can imagine the utility if you can scan with a microwave system and locate aircraft, especially if they're hostile to your interests. It's very useful to be able to see where they are and where they're going and plan your response accordingly. Let me go back here to our web presentation. So this is the point here is to sort of demonstrate the historical background from which radar came. Weather wasn't the original thing of interest in these radar systems. In fact, the World War II era systems were rather confounded when these irregular blobs of signal return would appear that tended to obscure things like the radar targets. But as World War II wound down, the fact that radars could see precipitation targets was of great use to meteorology purposes. So here's a redrawing of that earlier sketch, but now my pulse is directed at a raindrop instead of something like an airplane or a power line tower. But the same principle applies here. The short duration pulse is radiated out from a directional antenna. The microwaves interact with the water molecules in the raindrops, and they cause a faint but detectable signal to be re-radiated, some of which comes back and reaches our radar antenna site. So for weather radar purposes, in terms of precipitation, this is a little background on the drop size distributions that affect the signal that the radar receives. So customarily, we speak of the number of raindrops that are located within a cubic meter of air. So to give a sense of how big that is, this is a cardboard box I happen to have at home, and I did not have a 1 meter box. This one is just about half a meter on a side. So you can imagine a 1 meter sample of air would be something you could, if you held, you probably couldn't see over the top of it. You know, it's a fairly big size box in terms of physical volume. And to get an idea of the size of drops that are out there, depending how sharp it is, a typical number 2 pencil, if you sort of peck at a piece of paper, the marks you'll make will be pretty close to 1 millimeter in diameter. And for this kind of a elementary school type pencil, if you look at the eraser on the back end of it, that's something on the order of 6 millimeters in diameter, which is about as big as raindrops get. If they're larger than that, they become unstable and break up into smaller sized particles. So when we're trying to get an idea how strong an echo precipitation targets return, we're thinking of the number of drops that are in a cubic meter volume. So keep this sort of physical construct in mind here. Here are 2 distributions I plotted up for heavy and lighter rain. The one on the left is showing heavy rain. The horizontal axis here is the diameter category of the drops. And so these 1 millimeter diameters down here are like the pencil point end sort of a size, and the big eraser size ones are out here in the 5 to 6 millimeter range. The vertical axis is the number of these drops that would be in a cubic meter volume of air. And you notice characteristically we have a large number of the small drops. So here, like at the 0.5 millimeter size category, we have about 2,200 drops in a heavy rain case, and that number decreases quite dramatically with size. So if we get up to 2 millimeters, we have only about 200 drops. That's only a tenth as many as we had at the small diameter end, and so forth, on out to just a couple of these big 5 millimeter drops. The intensity of the signal that comes back to the radar for these water drops at the sort of radar wavelengths we're using, the scattering physics, if you will, causes the intensity of the received signal to be proportional to the diameter of these drops raised to the 6th power. So you can see a few drops numerically small in number, even though their diameters are big. If you multiply this diameter up times itself 6 times, you get quite a big number. So for this distribution here, if I raise these diameters to the 6th and sum them up, I come up with this very big number, 196,800 and so forth, which is a number of a larger scale than we like to think about as humans. So typically, the practice is to take the logarithm of this number and multiply that by 10, and we get this quantity known as dBz. You don't have to worry so much about the mathematics. The main thing is, by taking a logarithm, we reduce this number of 196,000 to a number like 52, around 53 dBz. I can also calculate how hard it's raining. This kind of a population of drops would be producing a rain rate of about 4 inches an hour. So this would be filling the center tube of your CoCoRaHS gauge every 15 minutes, which would be a distinctly heavy rain. On the right here is another drop population for much lighter rain. This only goes out to about 2.5 millimeters. You can see the number of drops in a cubic meter is much smaller. This, put on this dBz scale, this summation of the drop diameters to the sixth is about 34. And the rain rate here is not quite 1/4 of an inch per hour. So we take the power measurements that weather radars make and apply calibrations in the radar to produce this reflectivity value expressed as dBz. Here's an example of that happening at the CHIL radar. So again, this is a series of fixed images, but you get a sense that the radar is scanning around the horizon, and with colors here we're representing these dBz units. Here's one of the frames of this picture frozen, and the two reflectivities in those sample drop distributions we just looked at are here. So 53 dBz is this purple color. It's between 50 and 55 the way we color things, and farther out part of the thunderstorm in the less intense area, reflectivities are in the 34 category, which we code as red. So again, this is just processing the strength of the signal that comes back to the radar site, but by knowing where these things are in azimuth angle around the horizon and distance in range, we can plot a very accurate map of where the thunderstorm is located at any particular point in time. And again, this is possible at night, or if I had intervening clouds or fog or something to prevent me from seeing that thunderstorm optically, I could still make quite accurate measurements with the weather radar by these microwave backscatter methods. Reflectivity is not on any sort of universal standard. Here are two reflectivity images from the National Weather Service. The one on the left is from the National Weather Service radar at Little Rock, and I tried to highlight here their color scale, and these numbers are this dBz unit we just talked about. And you can see that there's an area of thunderstorms moving into the northwest of the coverage area of the Little Rock radar. This is a grab from about the same time from a television station in Little Rock, and they're processing the numbers at all on the scale here, and often for television presentations this is the case. The colors just are listed as heavy or light. The Weather Service, if it gets up to 70 dBz, uses purple colors, but the television presentation, that would be confused with this mixture of rain and snow, so they would just never get out of something that would be red for a very intense echo. Different presentations of the same basic information. We can also collect data with our radar, and many of them, although not the Weather Service, do what we call range height indicator scans. This is where we stop the antenna at a particular point around the compass and change the elevation angle. So we're moving the beam here that the antenna is focusing and sending out, so it samples a vertical slice of the atmosphere, and that gives us useful presentations like these. On the left is a photograph I took at the radar site of a thunderstorm, and this is an RHI scan at just about the same time. So the antenna, the radar is behind me as I'm taking this picture. We stopped the antenna at an azimuth of 150 degrees, which is a little south of southeast, and that corresponds to a vertical slice right about through this part of the storm here. So again, the horizontal direction is range, so these are in kilometers. I've zoomed in here. This is 20 kilometers and out to 50 kilometers from the radar, and these are heights above ground. Again, the quantity is reflectivity, so we can see these strong reflectivity values reach up to a number of kilometers above the ground. In fact, the height of the echo here is works out to about 44,000 feet above sea level. This is again because the vertical motions are so strong in these convective storms that large particles that return a strong radar signal are being lofted up to these very high heights, like we see visually looking at the cloud. The one on the lower right is an RHI scan through a winter precipitation case, and two things are apparent. The height of the echoes is much lower here, with a top at about 24,000 feet. These are plotted with the same units on the color scale here, and the snow doesn't get out of the yellows. So the reflectivity values are only in the 30 dBz category. This is very typical of winter. The ice particles, this is all completely snow in this case, are not as reflective to the microwaves as the liquidation of those things means this return signal to the radar is not as intense as in the thunderstorm, but snow echoes of this intensity will cause many problems with highway travel and closing airports and so forth. So just as a historical reference here, I scanned these pictures from a textbook that showed some figures from the 1950s. This was where this radar technology began with equipment of immediately post-World War II vintage. Here is the way the radar data was originally displayed. These are all analog oscilloscope cathode, hardly even color televisions at this time. So the reflectivity displays of that era were just on these black and white presentations. You can see, trying to judge the intensity of this kind of shadowy picture is rather difficult. This was all that the Weather Service or anyone else had through the 50s, and it's a demonstration of how far we've come with the current technology, where even on television we're able to see these color contoured displays of the signal reflectivity. We'll move ahead now to the second measurement type in our list. This is the velocity measurement that we can make, I've said here, beyond the measurement of reflectivity. And this is a little sketch to sort of indicate the principle behind this measurement. Here's a thought experiment at the beginning. You are near the beach one day. You're over here on the left side, and over here the tide is coming in. And being curious, you wonder how fast the tide is coming in. So you look at your watch, and on the hour, you step over here towards the water. You carefully make equal length strides, and you pay attention and count the number of steps it takes to go out, get to the water, and come back. You keep note of that number of paces in your mind, and sometime later, let's say 10 minutes, you repeat that experiment, and you find out it's 4 less paces to get out here to where you reach the water at the second time than the first. So if someone asked you, you could say the tide is coming in at a rate of 4 paces every 10 minutes, which is not a very standard unit of measurement, but your procedures would be fine. So when we're trying to make this measurement with a Doppler radar, we replace our carefully equal steps by knowing that we're sending nice steady wavelength pulses from the radar. So the trip that the radar pulse makes out to the target and comes back, you can think of that as a distance of travel that amounts to so many wavelengths in terms of progressing through space by the radar signal. We don't really care how many steps it takes to get out. I mean, you just knew that the number changed by a factor of 4 steps between your 2 measurements. And in the same way, we just want to know how much of a wavelength the distance to our target changed by between pulses. And it's easier to make that measurement with the radar by considering the phase of the signal that comes back. So a full wavelength of the radar is a complete cycle. That's 360 degrees. You're kind of going around and repeating the same thing after 360 degrees. So if we compare the signal that comes back to a stable reference that we make, we can measure this phase angle that comes back from each signal reflection that comes back from the target. And these are the same way you made your measurement twice here, 10 minutes apart. We're measuring this phase angle every 1/1000th of a second. Now that may be easier, I hope, if we have a calibration experiment at the radar. So we have a lightweight styrofoam sphere here that we've covered with foil, and we're about to let it go on a weather balloon. This provides a nice, well-behaved, known target for the radar to observe. And over here are 10 successive pulses during which the radar illuminated this sphere as it was floating away with the wind. The counter up here shows the number of pulse we're looking at. So things begin over here on the right at number 1, 2, 3, and so forth. Clock face, the information, the origin is right here at the middle of the plot, and the angle that this line appears at is the phase angle of each signal that comes back from the flying sphere. Phasor line, as we call it here, moves through almost a constant angular step each time. And what this means is the distance out to the sphere flying away from the radar is changing by a very steady fraction of a wavelength every 1,000th of a second. And so since we know the time difference between these illuminations and we know the wavelength of the radar very carefully, we can convert this sort of phase change between every pulse to a measurement of how quickly the target is moving either towards or away from the radar antenna. The length of this line here from the origin out to where my X is carrying the reflectivity information. So the distance out here is how strong our target is, and the way this phase changes between each pair of pulses is how fast it's moving towards or away from us. The direction that the phase line rotates, in fact, tells you the towards or away motion. I know in this case the balloon is going away from us, so this rotation in a counterclockwise direction means our target is going away from the radar. The ability to make this so-called pulse pair estimate of the velocity was tested by research radars like the CHIL in the 1970s, and this was what was implemented by the Weather Service in 1988. The current National Weather Service radars, as you probably know, are called WSR 88D systems. That 88 is because that's the year that this technology was adopted. We learned after making these Doppler measurements that from an operational standpoint, the most useful interpretation of the velocities was usually by considering their geometric arrangement. So in the left panel here is a plot of radial velocity. Now, I've superimposed on it these arrows which indicate the Doppler measurement. Again, the main point is these are radial velocities. The radar can only see the motion component that's directly towards or away from the antenna. So all of these arrows are lined up either towards or away from the antenna. The radar, these are distances west and north of the radar. So the radar physically is down here off to the lower right. So directions away from the radar are these arrows that are pointing kind of up towards the top and the left, and the arrows that are pointed down to the lower right are moving towards the radar. And the colors behind here are showing the same information. Typically, or as a standard of reference, the negative numbers indicate motion towards the radar. And these brighter colors, or colors going from green to blue, are larger magnitude. So this is stronger motion towards the radar. 0 means no motion towards or away from the radar, and the positive values are away. I've drawn the circle here near a mesocyclone circulation. So where this circle is, you see on this side of the circle, the underlying colors are positive. The arrows indicate motion away from the radar. And on the other side of the circle, that's reversed. We have negative quantities shown here by the colors, and the arrows indicate motion towards the radar. So this is the kind of pattern that when the forecasters see, you will hear in the warnings that National Weather Service Doppler radar indicates a possible tornado. This is a larger scale circulation than a tornado, but earlier in the life cycle of this storm, there was a tornado reported. On the right is the reflectivity pattern for this same sweep of the antenna. And you can see there's a suggestion of a hook echo pattern in the reflectivities here. There's very strong inflow towards the storm is causing this notch, sort of indentation in the echo pattern. And the inbound side, due to the mesocyclone, is this protuberance here into a kind of a hook echo pattern. In this part of the echo over here, you can see a convergent pattern in the radial velocities, because here strong motions away from the radar are colliding with strong motions towards the radar. So since this is at low elevation angles near the ground, we can infer there probably is if urging under the storm, and it is being exhausted, if you will, up in the vertical direction. Before I leave this for scale, this red line here at the bottom is 1 statute mile. So you can see that, you know, this rotation is under like 1 square mile farm field, sort of a size scale. The next slide is another example of the same thing. This is the opposite of what we last saw. Here the radial velocity is showing a pattern of divergence. Here's east-west direction, so the radar is 15 kilometers due south, right down here somewhere. Again, the arrows are lined up directly towards or away from the antenna, because that's the only measurement we can make. On the near side, we have strong motion towards the antenna. These blue colors are on the order of 12 meters per second. If you double this number, you get knots. So this is about 24 or 25 knots towards the antenna. And on the other side of the storm, we have slightly weaker velocities away from the antenna. So this is, you know, 20 knots away, 25 knots towards. Again, this is happening over a scale of about 2 miles, which is about the length of an airline airport type runway. Much interest in these sort of velocity patterns exists in the aviation community. Attempting to take off or land in these sort of diverging wind fields when you're near the ground is very destabilizing to aircraft and can lead to accidents. In fact, this is a sketch by Ted Fujita, who was one of the early workers in this area. Here's a thunderstorm producing a precipitation shaft, a strong downdraft which reaches the ground and then spreads out more or less symmetrically. But because our radar measures only the radial motion, a radar looking along the line I've sketched in here would see away motion on the far side of this and towards motion on the near side. So that's exactly the pattern we have here, near on the close side and away on the far side. Here's the reflectivity pattern. Again, there's the strongest reflectivity. The large particles falling out of the storm are right here in the middle, and that precipitation column is driving this outward wind flow. Again, we don't see this is air motion is cutting across the antenna beam direction, and so we're not able to see that towards and away pattern on this side, these sides of the system. Okay, this brings us to the radar technology. Like I said, it was adopted by the Weather Service in the late 1980s, which is dual polarization. This is sort of a lead-in slide to the concept of what's going on here. When we talk about polarization, the direction we speak of is the direction that the electric field in our microwave pulses is vibrating. And this isn't true just of radar signals. For example, here antennas often can tell you the polarization of the signal that is being picked up. Here's a television antenna, and the elements on this antenna are in the horizontal plane. And that's because not always, but the standard polarization that's used for television transmission is to have the electric field vibrating in the horizontal plane. So if you want to pick up the maximum of the television signal, you have your antenna oriented horizontally. Here's a little communications antenna at the radar, which is vertically polarized. So the elements on this antenna are positioned perpendicular to the horizon because the voice communications we get over this frequency are transmitted with vertical polarization. So in the case of the radar, we control the polarization that we're transmitting by what we call the feed horn. Here's a picture of 2 feed horns we use at the focal point of the antenna. Their job is to take the microwave energy from the transmitter that's coming through these waveguides, which are hollow transmission lines like you see here, and couple them efficiently into the atmosphere. So the back end of a dual polarization feed horn has 2 waveguide connections. And depending which of these ports, as they're called, we put the microwave energy into, the feed horn will determine how the electric field is vibrating as it gets radiated out of the end of the horn. And in this case, If I put microwave power into this port here on the bottom of this particular feed horn, that means what comes out the front end will have the electric field vibrating in the horizontal plane. And similarly, if I energize this port, my pulse is going to go out with the electric field vibrations in the vertical plane. Now the same thing happens on reception. The signal that gets backscattered to the antenna lands on this reflector. It goes to the subreflector in the case of our antenna, and then it re-enters the horn going towards the radar receiver. And that signal that lands on the face of the horn will be separated into horizontal and vertical components by this feed horn. So with a dual polarization feed, we can control the radiation, the polarization we're sending, and we also separate out the polarization components of the signal that comes back. Well, why would we be interested in doing this? The reason is by being able to consider separately the horizontally and vertically polarized signals, we can get information on the shape of what we're looking at. So here's an animation that shows the equilibrium shape of raindrops. They're going from small diameters, 2 millimeters, a little bit bigger than the pencil point, up to the pencil eraser size. And you notice as the drop sizes get bigger, the equilibrium shape, as these drops fall, gets more oblate, more flattened. This comes about because the falling drops experience aerodynamic force of the air whooshing past the drop as it falls, and that's being counteracted by the surface tension that tries to draw the drop into a nice spherical shape. So if we look at a drop while we're alternating the polarizations with the radar, we get a stronger signal if we have oblate drops in the horizontal illumination than we do in the vertical illumination, because you remember the signal strength is proportional to the diameter to the 6th power. Well, for a drop like this, the diameter in the horizontal direction is a bigger number than the diameter in the vertical direction. So this first polarimetric measurement we're talking about, which is differential reflectivity, often abbreviated ZDR, we just take the ratio of the horizontally polarized reflectivity compared to the vertically polarized reflectivity. And once again, we put this on a logarithmic scale. The main thing to remember is, in terms of logarithms, if these two numbers are the same, so we're taking the ratio of a 1, then we get a 0 for the logarithmic ZDR quantity. Here's an example to illustrate how this affects our radar measurements. These are a series of raindrops observed in a wind tunnel, and you can see their diameters get bigger. So this one is 2.7 and 5 and so forth, up to this whopper here that's 8 millimeters in diameter. And as we saw in the last calculated drop shape example, these get ever more oblate. They look something like hamburger buns with a flat bottom and this kind of dome-shaped top when they get big. And on the top of each panel is the calculated differential reflectivity. So you can see as the numerator is getting bigger here, a big flat drop like this has a much bigger horizontal polarization reflectivity than vertical. And when you put it on this logarithmic scale, you get a number like 6 dB, a fairly big positive number if it's a big flat particle, and a very, modestly small number if it's just barely deformed. And as they say here, for very small drops under a millimeter, they're so nearly spherical, this ratio goes down to 0. Now the 0 ratio is also true typically of hailstones. They don't deform as they fall because the ice is too resistant to the aerodynamic forces. And also, as indicated by these arrows, we have quite reliable measurements that many hailstones tumble as they fall, or they gyrate through quite large orientations. So even if they're not perfect spheres, if you look at a series of H and V illuminations, they will average out to pretty nearly an equal power on both channels. So this characteristic lets us distinguish rain from hail with a dual polarization radar, and here's an example of the CHIL radar doing just that. The left image here is our reflectivity. This is dBz, the quantity we first looked at. At a low angle scan, the elevation here is 1 degree, and we're sweeping through a thunderstorm which is moving over the city of Fort Collins, actually. These numbers, again, I changed the colors because there's no universally agreed upon way to present this, but these colors that get into the sort of pinkish red and bright red are in excess of 60 dBz. Very strong signal level. On the right is the differential reflectivity from this same sweep of the antenna. So again, this is the ratio of the horizontal signal compared to the vertical signal. And 0 is down here in these pale green colors. And you can see I've drawn a little irregular boundary around the center part of the echo. So this very strong signal is due to particles that don't have any preferential orientation. We're getting very nearly the same power on H and V. Surrounding that, there are other parts of the echo where there's quite a difference. You see the numbers go up in the positive direction. This indicates these are preferentially horizontally oriented particles. So there may be a few hailstones mixed in here, but this is mostly heavy rain where the differential reflectivities are positive. In the heart of this particular storm and this particular sweep of the antenna, there may well be rain, but the signal is being dominated by all the hailstones that are in there. Now we got verification in this case that this spot marked 834 was the CoCoRaHS observer. And this storm was in fact moving from south to north. So this intense area of reflectivity with no preferential orientation went right over this hail pad. And you can see we have all the classic sharp edge denting, and in this case this observer was very dedicated and changed the hail pad in the course of the storm, and the second pad received tears in the hail due to the vigor and size of the hailstones. So differential reflectivity can be quite useful in distinguishing where in a particular thunderstorm in the total sense the dominant returns due to hail are located. So you can imagine if you're issuing warnings for storms, this kind of ability to distinguish particle shapes is very useful. Here's another example of target discrimination. This is a different case. The radar is converge. We're looking at a thunderstorm to the northwest of the radar. So once again, this is the conventional reflectivity getting strong into the 50 dBz category. There's an area very weak, essentially no signal, then another sort of ring of lighter intensity echo out ahead of the storm. By considering the differential reflectivities, we can see at least 3 different regimes. This area here, where I've indicated with an arrow, are raindrops, because the differential reflectivities are getting up in this few dB positive range. If you look along this one dashed azimuth line here, you can see there's a positive association. As we get into the stronger echo here, going up in the reflectivity scale, the differential reflectivities go up. So this is mostly raindrops that are falling in this part of the echo. In the middle part, we see the hail signature. Again, this sort of S-shaped area has very high basic return signal intensity and no preferential orientation. The H and V ratio is way down here near the 1 range. And the highest differential reflectivities of all are in this band out ahead of the storm. This is as high as we can measure. This is 9 dB, and from many investigations we know that this kind of a signal return is due to flying insects. You can see the body shapes of these insects are a lot flatter than the raindrops, so the ratio of H to V is a very big proportion. The insects have enough liquid within their body fluids that they act like a reasonable approximation of a raindrop. So we can't tell too much from just the reflectivity pattern about where the different sorts of echo categories are taking place here. I mean, there's something strong here and there's something weaker pushed out in front of it. With the ability to measure differential reflectivity, we can say that there's dominant hail in the middle part of the storm here, ordinary rain here, and non-meteorological targets. This isn't rain at all out here. This is predominantly insects out ahead of the storm. Okay, the second of the 3 polarimetric measurements I'd like to talk about is so-called differential propagation. And here's another one of these little thought experiments to try to get an idea what's going on here. Here we have a sketch of 2 identical twin brothers, Victor and Horace, who are taking a hike in the winter. Their legs are the same length. They stride just at the same rate. You know, they do everything the same. The difference is only Victor has a pair of snowshoes on, and his brother Horace doesn't. So they start out from the left side here, and they're marching along, and initially they keep pace with each other pretty well. But when they get into the part of their journey that goes through deep snow, Horace has a harder time because he doesn't have the snowshoes. So the point is here, his rate of propagation through the snow is different than his brother Victor. And as they march through the snow with every step, Victor makes a little better progress than his brother Horace. So the gray line here shows, if you will, the phase difference between where they are each step of the way. And that difference gets worse and worse as they're trudging through the snow. Then when they leave the snow field, if Victor is impolite and doesn't wait for his brother, they just stay at this constant degree of separation. So from looking at how their positions vary, we can, if you will, in retrospect, we can say, well, the deepest snow must have been right here where these S's are, because they tracked pretty well. Then in this part of the trip, Horace steadily fell behind Victor. It got worse and worse and worse and worse. Then that difference didn't change after that. So the heavy snow field must have been right in this area. Well, of course, with microwave radars, we're not dealing with snowshoes and people marching around, but we do measure the phase of the return signal, as we saw for the velocity measurement. And so here's the sort of propagation effect shown in terms of the radar waves. Here's a set of heavy raindrops. This is direction, range direction away from the radar. And our H and V waves we're sending out, let's suppose, have some phase difference. They don't line up perfectly, but that's all right. We're only interested in the change in the phase. So here are the two waves approaching this area of heavy rain. And because of the scattering effects, after we go through this area of heavy rain, the horizontal signal will be lagged, just like Horace couldn't keep up with Victor due to the snowshoes. The propagation characteristics of the H and V waves are different, and it leads to this shift. So areas where H falls behind V, we can say must have heavy rain going on, and here's an example of that. So on the left is a reflectivity image. You're becoming more and more familiar with these sort of measurements today. So here's our DBZ scale. Constant range rings from the radar. The radar's off to the left side here. So here's an intense area of rain, and even though I don't show you the differential reflectivity, there was hail mixed in with this rain. Here's the same sweep of the antenna, only now the colors are showing the phase difference between the H and V signals. And so there's some angular difference represented by these green colors at the bottom of the scale. And as the waves go through the first part of the storm, those colors don't change very dramatically. But then when we get into the very heavy rain area, the H signal increasingly lags the V signal, and that's represented by movement up this color scale. So with short distance here, we go from dark blue to light blue to white to pink to red. So here's dark blue, light blue, white, pink, red, and so forth. And then as we get to farther ranges, the colors sort of level off, and we stay in this yellow region. The plot on the top here is sort of a line graph along one direction from the radar antenna, showing that same thing here. The red trace is the so-called differential propagation phase. To begin with, the number is steady, so this is like Horace and Victor keeping pace with each other. Here, the line steepens up, because this is the part where, as we go along in range, the H is falling ever farther behind the V in terms of phase. And then after we're done with that, we level off at this new, after the shift has occurred, sort of a number. So the real quantity of interest here is the steepness of this slope. Those of you who are calculus fans will remember the derivative. So if you can fit a slope to this phase line, we can calculate or estimate how heavily the rain is falling here. And this slope here turns out to be about 4.7 inches of rain per hour. The nice thing is this phase today is what is known as the correlation coefficient between the H and V signals. And basically, if you look back to what we've talked about today in the way of polarimetric measurements, the differential reflectivity, the first one we talked about, we were only concerned with the magnitudes of the H and V returns. This is the basic reflectivity, except one measurement is made at horizontal polarization and one is made at vertical. And this showed us where particle orientation effects were important, tumbling versus flat. The differential propagation effect we just looked at, we used only the phase information. We didn't care how strong the H and V signals were. We only cared about their phase relationship, one relative to the other. So it is possible to consider both magnitude and phase, and we can do arithmetic that produces this correlation coefficient, the so-called ρHV, or just straight. For the correlation is the highest when the radar is looking at particles that are pretty similar. So we're illuminating a collection of raindrops or snowflakes, and as the sketch here on the lower left indicates, if we have all snowflakes in the radar volume we're looking at, or if they're all raindrops, they're all pretty similar, this HV correlation is pretty high. It gets very close to 1. If the radar looks at a mixture of different shapes and sizes and orientations, then this correlation will be reduced. Here's an example of that. So here's an RHI scan, the antenna moving up and down in elevation. This data was taken at the beginning of a winter storm that was setting up here in Colorado. So the vertical axis is height. When this particular sweep of the antenna was made, the precipitation was still rain at the ground. So the colors here are correlation. These yellow colors near the top you see are very high, 0.98 up to about 1. And it's high up above in the upper part of the cloud where we're looking at entirely frozen particles, and the correlations are high down in the lower part where everything is melted out and completely become raindrops. And in the melting layer where we have a mixture of some drops that have already melted all the way and some that have are still frozen and probably wet and clumpy, you see the correlation goes down to these white numbers, about 0.9. So it's not a big change. We go from 1.0 to about 0.9. But still, this gives us useful information that the melting layer is right here. This is the reflectivity from the same sweep, and as these particles, ice particles, become coated with water, they become better reflectors. So we get a maximum in reflectivity right near that melting level as well. Here's a time lapse over about a 2-hour period. The rain changed to snow, and here we can see that being shown by the correlation field. So at the beginning of the loop here, we have this layer where the particles completely melt and become all liquid, so they get back to fairly high correlation. With time, the ground temperatures are cooling. We get to a condition of mixed rain and snow, and then as the night goes by, all snow. Weather Service forecast discussion, this is from New York City office back on January 16th, and they were noting that rain along the coast had changed to sleet per dual pole measurement. So this is from the operational National Weather Service radar in the New York City area, can use this sort of information to help the forecasters understand what sort of precipitation is falling in what geographical area. Another state of affairs that significantly reduces the ρHV is debris lofted by tornadoes. So here's a reflectivity pattern. Now this is my one example. It's not from the CHIL radar. This is from a shorter wavelength radar that was operating in Chickasha, Oklahoma several years ago. It was provided to me by my colleague here at CSU, Dr. Chandrasekhar. So this is the reflectivity pattern, and those of you who are familiar with tornadoes will recognize the very wrapped up hook pattern. So the radial velocities, which I'm not showing here, there's a very intense circulation pattern due to a tornado. This is the correlation field for that same sweep of the antenna. The majority of the echo here has high correlation, up in the neighborhood of 0.9 and higher. The interior region, right near the apex of the hook, you see a distinct lowering. This is down around 0.6 type correlation. And numerous research investigations have related this low correlation signature in the hook echo to debris that's being lofted from the ground up to where the radar can see it. So you can imagine if we talk about particles of different sizes and shapes and orientations, lowering the correlation, flying roofing material and building components and so forth are quite diverse and very drastically lower the correlation. This is a report from the Storm Prediction Center of about a week ago that I noticed in the remarks. This was a tornado report in Arkansas. And once again, dual pole radar data suggested debris in the air. Well, this is a remark from a Weather Service forecaster looking at this correlation field on a polarimetric National Weather Service radar. The conversion of the radars to dual polarization is shown on this plot, which I just grabbed few days ago. That are in green are already converted to dual polarization. So there is a team that's at the time that this plot was made, they were doing these three sites shown in here in yellow. They go to the National Weather Service radar sites, they install a dual polarization feed horn and a second receiver channel so that the radars can separately receive and process the H and V signals. And you can see they've been busy. The great majority of the country already, the Weather Service radars are making these dual polarization measurements. This little cluster here, and the reds and yellows are in progress, and the last few are out here in these pale unique hail identification, improvements in measuring how hard it's raining in the presence of hail and so forth, identification of tornado tracks and tornadoes in progress by the damage signature.
Pat, this is Henry. On that map, the spots where that are white, just is the radar not covering that area? So there's like in Minnesota and parts of Montana and so forth. Does that have National Weather Service radar coverage?
No, that's actually right. The underlying regions here, I should have looked at the details, but this shows where the radars cover at a certain height level above the ground.
Okay.
I think if you go up higher, the coverage is more continuous. But at the altitude they're showing here, there are some of these sparsely populated areas where no radar is able to illuminate that area.
Okay, thanks.
And that actually brings me, we're done in terms of slides, so I thank you very much for your attention going through all this, and if any questions Henry relays, I'll do my best to answer. Before I finish up here, on this particular slide is the website for the radar, the CHIL radar, and I'll supply Henry with some other websites that the webinar listeners might find of interest to learn more about these topics. And with that, I'm done. Thank you.
Thanks, Pat. That was really educational. I'm sure there's a lot of folks out there, or even some of us here, that didn't know all about a lot of this stuff, and really appreciate the primer on it. Hey, we've got a couple questions coming in. We're going to take questions for about 20 minutes. If you do have a question for Pat, you can type that in on the website. We'll try to get it to as many as we can. And Pat, our first one is from Jim from Maine, and he wants to know, do all National Weather Service radar sites record their data for a later review? I guess so folks can use it, or they can go back and archive it and look at it.
Yeah, they do. The data ends up, as so much of the National Weather Service data does, at the National Climatic Data Center in Asheville, North Carolina. And many people, myself included, make use of those archive files. So, after there's been a storm of interest, you can download the recorded data from Asheville, and it's It's excellent. It would be a shame to operate this many radars and not record the data for post-analysis, so that is done.
Okay. Chuck in Georgia wants to know is what is the effective range of a typical Doppler? So the distance on that, how far does that go out?
It depends partly on how frequently you transmit a pulse from your radar. I'm going to go back here to one of my earlier slides. So sort of fundamentally, you know, as we mentioned, the basic concept is you radiate a pulse and then you're listening for all the signals that come back as that pulse encounters objects along its way. So how far out you can detect signals depends on how rapidly you pulse the radar. The other aspect of the Earth. So even if we had the antenna set to horizontal elevation, when you get very far away from the radar, your signal is getting very high off the ground, and pretty soon you're above the top of even the tallest thunderstorm. So the effective range is usually on the order of 150 to 200 statute miles. Make any kind of detailed measurements at long ranges. And that's the reason the Weather Service has this network of radars. Each particular one, as you can see, only goes out to a fairly finite distance, and then you need a helper radar off over the horizon to keep watching for you.
State that you're from, that would be really helpful. Phil and also Marion both write in and wanted to know about the radar data that you just talked that was archived. One, can the public retrieve the archived data and the maps? And two, can these be retrieved in real time?
The archive files take address on what I send to Henry. I think they offer software. They basically provide digital format data files that you need software in order to decode, but I think they have some software to help read those files. I'm typing here. I guess I'm still sharing my screen. Personally, I like to use this Aviation Digital Data Service, ADDS website. They have a tab for the National Weather Service radar network in real time. And all you have to do is click, for example, in Chicago, there's some precipitation. This is usually the composite. Here's the lowest elevation scan of the Chicago National Weather Service radar as of a few minutes ago. So if you don't need the actual digital files that have all the numbers stored here in a machine readable format. You can see the images quite easily on the internet.
You know, Pat, I've used in the past, University of Iowa has put together on their Mesonet page a really nice archive. You can put in the date, the radar location, it goes way back a couple of years, and pull up a date, and I've used that in presentation. So that's another one to look at. We'll list these on the website, on our CoCoRaHS WxTalk website under references, and we'll put those URL links in there for you. A couple of folks here, and Ralph from Florida is one of them, wants to know if there's any thought to standardizing the colors using radar images. So, you know, you watch TV, they've got a different color. There's a color here, a color there. Any thoughts on that?
Well, I think if the short answer is probably no. If you always go to the same source, for example, all of these Weather Service images brought up by this site will use the same color scale. But you know, the television information is often provided by commercial contractors, and they like to differentiate themselves and so forth. So it's best if they at least provide the numbers, so you can say that whatever color they're showing is 40 dBz. But I wouldn't expect a national standardization to happen anytime soon.
Okay, Joyce writes in and she wants to know what is the difference between composite and base loops?
Well, the composite, actually what the radar is doing here is executing a volume scan. And the particular one they're running is shown by these little numbers here. They're using volume coverage of precipitation regime number 21. And you can look on the Weather Service website. That's a prescribed series of elevation angles the antenna will scan through. So it starts out usually at a half a degree, and they make a full sweeper on the horizon. Then the systems that are controlling the antenna will raise the antenna by a degree or two, and they'll make another sweep, and they'll step their way up to get more of a three-dimensional sampling of the atmosphere. So this composite map, they take the reflectivities at all those different elevation angles, and if you will, they squash it together. They take the highest value found at any elevation, and they code that up in their picture here. The base angle scan is just the lowest elevation angle only here. I guess I had the base selected. So here when I go to composite, you can see they're picking up some higher reflectivities that are above the lowest sweep of the antenna. If you watch this area north of Ottawa here, I believe if I go to the base, some of that high reflectivity is being seen at angles above the lowest scan of the antenna. So when you click on base, you're seeing just one elevation. When you click on composite, you're seeing sort of a summation of the highest thing seen on all the elevations that the antenna did.
Okay, thanks. Let's see. Here's one here from Brian in Maryland. He wants to know about calibration. Wonder if you could cover some stuff, the issues with dual pole calibration. It says National Weather Service has been struggling with calibration of both ZDR and initial phase system.
That's true, and we struggle with it also. These are, you have to pay quite a bit of attention to drifts in your radar equipment. Once you have a dual polarization radar with two receivers, of course, you know, one is doing H and one is doing V. If temperature effects, for example, cause the gain of one receiver to change relative to another, that begins to bias the ZDR measurements. And similarly, the phase between H and V, the sort of basic system phase, can change due to operating temperature and so forth. So in terms of the Weather Service radar and our radar, we inject test signals backwards. So, you know, we send a known signal level through the H and V receivers and monitor whether that response of the receivers is drifting with time. The Weather Service is doing it when they do these scans, like I've described here, from low elevation. They work their way up to some high angle, maybe 19 degrees. Then the antenna drops down to begin the next volume scan. And so while it's on its way down, the Weather Service is injecting a series of test signals into their receivers, so they get a measurement every few minutes of how those receivers are behaving. That helps catch big fluctuations, but as the questioner indicated, this is an ongoing system that's being refined by the Weather Service. So as good as as useful as these polarimetric measurements are, it's sort of a price you pay. They can be tricky, and it's an ongoing question, I guess. I mean, their efforts are made to monitor and do systematic tests of the equipment, but things can still get somewhat out of whack from time to time.
Okay, Tom from Ohio wants to know, do our CoCoRaHS observations and data help improve radar readings in any way?
Yeah, they've helped us at the CHIL. In particular, we have done measurements to try to, well, there's many ways you can try to estimate how hard it's raining from the radar data, but you really need, I'm going to type, that's why I'm talking so haltingly here. I guess this was in my memory column, but let me go back to my own website here. It's very useful to try to compare ground measurements to what the radar thinks it's measuring. I involve CoCoRaHS per se, but this was a case where we had a thunderstorm go over a rain gauge site operated by the city of Fort Collins, and that's what's shown down here at the bottom. So this is a tipping bucket gauge. You know, the size of the opening and everything is on the order of what your CoCoRaHS gauges are like, but this is operated by the city of Fort Collins. Every time the bucket tips in here, it telemeters a signal to the city to check for flash flooding conditions in the urban area. So we took some measurements from one particular day, and the blue lines here are times when the bucket tipped at that particular gauge I showed in the picture, and the dots here show the way we guessed the rain was accumulating from the radar. And of course, you know, we did fairly good, so we used this for our example here. But to answer your question, you know, many ways from the radar data. You know, there are different algorithms you can use, but it's very helpful to have ground truth measurements, like in this case a tipping bucket, but we've used rain maps in the past where we sum up the sort of rain pattern we think that the radar indicated should have happened, and then compare that with the reports that people like CoCoRaHS observers file. So you don't want to go too far in the radar business without getting some verification data, or you can lead yourself astray.
Lisa writes in, and she wants to know how important are spotters to helping with radar, like a funnel detected or a tornado Doppler rated Doppler detected tornado. How important are spotters in that sense?
They are important. One problem in almost every case, as I've said before, the radar beam generally is off the ground by some amount, and it gets higher up the farther away from the radar site you're located. So we do have cases where especially smaller diameter hail will melt on its way down to the ground. So the radar may indicate, and it's telling the truth, that there is hail present, but depending on the distance from the radar and the temperature and moisture structure of the lower atmosphere, that, you know, only your ground spotters can confirm that there is hail landing on the ground, and we still have a lot of uncertainty in categorizing the size of the hail. We can, you know, a forecaster can be suspecting he should issue a severe thunderstorm warning based on the radar only, but it's very comforting to get a spotter report that there really is 1-inch diameter hail versus half-inch or 3/4-inch diameter hail. We can't very well make that fine diameter distinction, at least not yet anyway. So still the spotters are really the gold standard, I would say, of what's happening. I know at the National Weather Service office in Denver, they they were demonstrating this to me. They have the capability to call up phone numbers of spotters by clicking on their Nextrad radar display, and they will solicit spotter reports if they think a storm looks suspicious due to large hail. They actively seek confirmation from the spotters, so they play an important role in this.
Thanks, Pat. Here's a question, actually two questions from two different people, Mike in Ohio and Eric in Golden. They're kind of related. Mike wants to know what is the smallest size particle is detectable, so what about fog? And then Eric in Golden says snow is a poor reflector. What other wavelengths or techniques like dual polarization resolve snow in all its forms and behaviors? So two questions, but talking about particle size and reflectivity.
Well, yeah, I guess that was one of the quiz questions. For these, as I say, the CHIL and the National Weather Service radars operate in the vicinity of a 10 to 11 centimeter wavelength. And for that wavelength of radar signal, fog particles are very difficult to detect. You might see faint indications at very close ranges to the radar. The answer to that question was supposed to be false. I mean, with a standard National Weather Service radar, you can't see you know, any sort of comprehensive mapping of where fog exists. Now, the intensity of the backscattered signal is inversely proportional to the wavelength. So shorter wavelength radars will get a stronger signal. And for research purposes, there are a number of radars that operate down in the 1 centimeter or a few millimeter wavelength type band of operation. And they see much more in the way of thin clouds and fog and these more tenuous sort of weather situations than we do. The downside is these, as you go to shorter wavelengths, the attenuation problems become larger. That is to say, the radar signal is weakened as it propagates through the precipitation. And so even though you can see things like fog more readily with a short wavelength radar, you won't be able to see very far through rain, for example. So you have a trade-off. If you have a longer wavelength radar, you can maintain surveillance over a large area. One storm will not cast a shadow that blocks out another one, but you won't be able to detect these non-precipitating things like fog and so forth. So the shorter wavelengths can help. Generally, historically, we've used the longer wavelength radars to try to get more coverage and suffer less from attenuation. So, yeah, you could customize your radar to better see very faint snow and fog echoes, but for most operational purposes, it isn't feasible to do that.
Okay, Abby in Los Angeles was wondering, are there military applications for this type of radar?
Dual polarization, I presume?
Yeah, I think that's what she's asking.
Well, I'm sure there are. Of course, they don't talk a great deal about what they're doing, but we, for example, can identify the polarimetric signatures of what's called chaff are quite distinctive. The military, from time to time, will release these little, they're kind of like mylar or tinfoil or tinsel, actually, like you might hang on your Christmas tree. And that is released to confuse ground-based radars. So they, if you're trying to hide your airplane from, for example, a missile or something that would try to lock onto you, you can release trails of chaff and you get a big sort of diffuse but strong target that might fool the ground instruments. The polarimetric signatures of chaff are quite different than at least meteorological echoes. So you might, I'm guessing here, you might be able to use polarimetric signatures to see through the chaff and find out where the airplane still is, for example. But let me add, I'm guessing as a civilian. There probably are things they can do with polarimetric measurements, but I'm not familiar with them.
Okay, let me see what we have. A couple more coming in here at the moment. What's next after dual pole? Russ from Illinois wants to know.
Well, that's a good question. Two areas of active research. We still, one of our biggest handicaps is that we're using mechanically scanned antennas. So as you saw in, oh, everyone is seeing my window here, my goodness. As you saw in the antenna motion examples here, antennas, especially as large as the Weather Service uses and we use, are difficult to move around. So, this is many thousands of pounds of aluminum and steel to the acceleration you can impose on this kind of a structure. So there is active research underway to do electronic scanning, that you use a different kind of antenna. Instead of focusing your energy with these metal surfaces, you, if you can imagine a sort of flat face antenna with many, many little emitters distributed on it, little dipoles. And if you phase those emitters properly, so your signal arrives at one part of the antenna at a different point in time than another part, the individual radiation from those diodes will dipoles will constructively add, and you can steer the beam around in space electronically, which you can do much faster than these mechanically rotating antennas. So there's a lot of research underway trying to get electronic scan technology to be operational. And when we can do that, we'll be able to collect data on a thunderstorm in less than a minute, let's say. You can snap your beam around and survey the whole ecosystem very rapidly. So for things that evolve fast like thunderstorms, it's easier and you can do a better job of understanding what's going on. The second area I would say that's developing is shorter wavelength. This gets back to one of the earlier questions, sort of small size radars that don't look out as far in distance as systems like the CHIL do. In fact, we're doing some research at our site. This little shadow being cast here is by a 3-centimeter wavelength radar, which is sitting on a flatbed trailer truck. So this has an antenna that's only about 7 feet in diameter versus our 30 feet. And research is underway to use networks of these smaller, simpler radars versus a less dense network of these big long-range radars like the CHIL. If you use the little radars, the radiation you're sending out can be kept close to the ground. You only may cover out for maybe 30 to 40 kilometers from the radar site. So the short answer to your question is I think electronically scanning radars and increasing use of these small, simpler network radars, I think, are the applications that are coming. Both of those will probably be dual polarization.
Well, Pat, thank you once again. A really great webinar today. We really appreciate your taking the time to come over and present this information. For those of you we couldn't get to all the questions today, but Pat will follow up with you on email and answer the questions we didn't get to answer. I want to remind you guys, we have a special webinar coming up in collaboration with NASA. It's going to be a free public informational webinar on next Wednesday, the 13th. And if you go to the CoCoRaHS Message of the Day, or when you put in your message, you'll be able to sign up for that webinar. And that should be talking about the Global Precipitation Measurement Satellite Mission. So some interesting stuff there. And then next month, actually 1 month from today, on March 7th, Mark Savoda, who you may have heard on NPR, he's been on there many times, of the National Drought Mitigation Center in Lincoln, will talk about drought, its impacts, role we play in that. And so that's exciting. We already have that up on our CoCoRaHS WxTalk webinar series website. You can sign up for that. We'll be sending some messages out as well. So please take the survey when you sign off today.